So good evening, everyone. I'm Calvin Joseph, and today I'm going to present week two problem solving and doubt clearing session for the course state space analysis of control systems and design. And I will be talking about various stuff such as what is a state space representation, how do we convert it into transfer function, how there are various state space representations are possible, and how do we transform a transfer function into those various state space representations, as well as we will be seeing some MATLAB codes and demonstrations which will help us, to verify our answer. Okay. So I will start. So this is the week two course, and we will first see, we know what is the state space equation for a linear time invariant system. Okay. So that is given by this x dot is equal to ax plus bu, y equal to cx plus du. Okay. Now, how do we proceed? Like, what do we do with these set of equations? So first of all, this representation is not unique. It is not unique. It's not a unique representation. There can be multiple representation. Let us consider this is the representation of, or like a S1 type of representation. We can have another S2 type of representation, which is given by z dot is equal to a bar z plus b bar u, y is equal to c bar z plus d bar u. Okay. So what is remains the same? Y and u remains the same. Okay. Only the state x instead represented by the state z, and hence the matrices or ABCD matrices are converted into a bar, b bar, c bar, and d bar. Okay. Okay. So Srikanth, is it audible and clear? Okay, so what do we know is that we can get a transfer function from this. So the transfer function which we are interested in is a transfer function of the output with respect to the input. Okay. So this transfer function is the same for system S1 or S2. So S1 or S2 is the same system. There's the same input, same output, but the representation is different. Okay. We represent one S1 with the state X, and we represent this S2 with the state Z. So the representation, state space representation is different, but the transfer function is the same. So that's why Sir has taught in this week, like he has taught first canonical form. Okay. He has also taught second canonical form, and he has also taught Jordan form. And diagonal matrix, etc. So there are like three forms Sir has shown. Also, there are ways in which we can convert one form into another form using a transformation matrix. Okay. There's something known as a transformation matrix, which we can use to convert one representation into another representation. All right. So all this was taught by Sir. And in the previous week also I had showed for two systems, that is the series RLC and for the op-amp filter, how the transfer function remains the same, though there is a different state space representation. Okay, so now mm, the various things we must consider. Why are we interested in the transfer function? Like we were considering what is the state vector, right? State vector x. Then why do we want the representation in terms of transfer function? The reason is like a transfer function is very well known, understandable way to represent the behavior of a system. Sometimes from one point to another point, the only information about the behavior of the system is we have a transfer function. So how do we convert? So how do we convert this x dot is equal to ax plus bu and y equal to cx plus du into a transfer function representation? Okay, so what is done is we apply the Laplace transform. So a point to keep in mind is the transfer function is a frequency domain representation of a system. Frequency domain representation. Okay. So what do we do? How do we take a Laplace transform? So if you will know that for x dot actually is what? Dx by dt. The Laplace transform of dx by dt, Laplace transform is given by s into x of s minus x of 0 minus. So this is the initial condition. So when we are considering the the transfer function, what do? We consider the initial condition is set at 0. Okay, we consider it to be set at 0. And then we will proceed. So now, so this x dot is equal to ax plus bu. We get it at s into x of s is equal to a into x of s plus b into u of s. Okay, this is in transfer function representation. So this we can write it as s x of s minus a into x of s is equal to b into u of s. This we can write it as s into I minus a into x of s equal to b into u of s. So I is your unity matrix. Okay, this unity matrix depends on the dimension of x. It depends on the dimension of x. Okay, I will show like how we can use the state space representation to get the transfer function of a system. Okay, we will consider that. So now what do? We pre-multiply it by si minus a inverse into si minus a into x of s is equal to si minus a inverse into b into u of s. So si minus a inverse into si minus a is your unity matrix I into x of s is equal to si minus a inverse into b into u of s. So your x of s is equal to si minus a inverse into b into u of s. Now we got x of s, but we want it in terms of y of s. So we know y is equal to cx plus du. So now we take the Laplace transform, what do we get? We will get y of s is equal to c into x of s plus d into u of s. We will substitute x of s, so y of s is equal to c into si minus a inverse into b into u of s plus d into u of s. So we take u of s common, so we get y of s is equal to c into si minus a inverse into b plus d into u of s. So what do we get? Your y of s on u of s is equal to c into si minus a inverse into b plus d. Okay, this is your g of s, or this is your transfer function. Okay, so this is your transfer function of the system. So now we can see like how from your matrices, from your ABCD representation, we can get the transfer function of a system. All right. So let us take an example. Okay, so sir has shown how he has converted it into the transfer function representation. Okay. All right. So I will just show a simple example. Let us consider some system. Okay, like let us consider some A and B and C and D. Okay, let us consider A to be minus 1, 0, 0 minus 2. B is equal to 1, 1, and C equal to 1, 0, and D is equal to 0. So we need the transfer function of this. Okay, so you can take this method. You'll have to do this. So what you have to do in this case is you first have to, your I in this case is a 2 cross 2 matrix. Okay, so you have to take S into I minus A. So that is S into 1, 0, 0, 1 minus A. That is minus 1, 0, 0 minus 2. Okay, so that we write as S 0, 0, S minus minus 1, 0, 0 minus 2. So this we get it to be S plus 1, 0, 0, S plus 2. So this is Si minus A. Now we have to find the inverse of the matrix. Okay. So now inverse of a matrix is a computational thing and it takes time. For 2 cross 2 matrix, there is a shortcut to find the inverse. Okay, suppose we have a 2 cross 2 matrix given by, let us say, A, B, C, D. Okay, its inverse is given by, you have to interchange this. The diagonal elements you will interchange. So this will become D, this will become A. And the sign of these non-diagonal elements will become interchange, will become minus B minus C, divided by the determinant of that matrix, that is A, D minus B, C. Okay, so this is a simple way. So you don't need to actually go find the adjoint and the cofactor and co-prime and other stuff. You don't need to do. You just need to use this formula. So you'll get the inverse of the. So this for the formula for inverse of a 2 cross 2 matrix. Okay, so now what do we have to do? We have to use this formula. So we have to find the inverse of Si minus A. So the inverse of Si minus A inverse, it is what we have to just interchange D and A. So this will be S plus 2, S plus 1. And since 0 and minus no factors, so it is S 0 and 0. Divided by the determinant. That is A into D minus B into C. So it is what? S plus 1 into S plus 2 minus 0. Okay, so Si minus A inverse actually is S plus 2, 0, 0, S plus 1 upon S plus 1 into S plus 2. So if you notice, this also is a 2 cross 2 matrix. This also is a 2 cross 2 matrix. And this term, this is the assignment, this is actually Si minus A. Okay, this actually is the determinant of Si minus A. And if we set it to 0, that means we set S plus 1 into S plus 2 is equal to 0. So this is known as what is known as a characteristic polynomial of the system. So this characteristic polynomial is the same for various state space representations. As the transfer function remains the same, even the characteristic polynomial also remains the same, regardless of the different state space representations you use. Okay. So now we got Si minus A inverse. Now what do we have to do? We have C and D is 0 and B is 1, 1. So our transfer function G is what? C into Si minus A inverse into B plus D. Now D is 0. What is our C is 1, 0 and B is 1, 1. So our C is 1, 0. Our Si minus A inverse is S plus 2, 0, 0, S plus 1 upon S plus 2 into S plus 1 into B, that is 1, 1. Okay. So what happens now? This is what? One row, two columns, two rows, two columns, two row, one column. Okay, so one row into two columns become one row into two. So this becomes 1 into S plus 2. So S plus 2, right? 0 and 0 goes. 1 into 0, 0, 0 into S plus 1, 0. So this becomes 0. This into 1 and 1. Divided by S plus 2 into S plus 1. Okay. Now we multiply this, it becomes S plus 2 upon S plus 2 into S plus 1. So effectively it becomes 1 upon S plus 1. Okay, so this is how we found the transfer function of the system. Any queries in this? Of how do we do this? Okay, so what I'll do is I'll just show a simple MATLAB demonstration. So what do we have? We our A is equal to what? Minus 1, 0, 0, minus 2. B is equal to 1, comma 1. And C is 1 and 0. Okay. So let me run this section. I will run this section. So what do we get? So my A is given like this. This is A is minus 1, 0, 0, minus 2. My B is 1, 1. And my C, sorry, my C is 1, 0. Now I want to find a transfer function. So I use this code. I set define S as a transfer function variable. Okay. I define S as a transfer function variable. Then I find a transfer function G. Okay. Also, I need to remember D is 0. So my G is equal to, okay, let me go one by one. So now I've defined S is equal to transfer function of S. Okay, so S is a continuous time transfer function. S. Now I want to do Si minus A. So my I in this case should be E by E2. Okay, this is my I. And it should be of 2 cross 2. So that is given by E by E2. 2 says it should be a unity matrix with 2 rows and 2 columns. Square matrix, square unity matrix, dimension 2. So now S into I minus A. So it comes in this format, okay? Also, if you want to find the inverse, the formula is INV into S into I minus A. So this is the inverse, Si minus A. So now let us find the overall transfer function. We will give it as C into S into EYE2 minus A into B. Okay. So let me run this section. Let me run this section. And when I run this section, I get this transfer function. For this inverse, I forgot. Let me run this section. So I get it as 1 upon S plus 1. Okay. So this is how we can use MATLAB and verify our commands, our code, everything, or our answers. Because you need to know that whether you do multiple calculations, you have made so much of hard work and everything, and then you don't know whether it's correct or not, right? So that's why I thought that this is a way for you all to, try to understand and try to be able to check whether your answers are correct. Okay, so this is how we can get the inverse, and we can use MATLAB also for it. Now, let us try the first method known as the first canonical form of a system. So we will consider a simple system. Let us consider an example, g of s. Okay, this is s plus 2 into s square plus 4s plus 6. Okay, assume it is like this. This is our transfer function. To make it a little bit more challenging, let us make it s cube plus 3s square plus 6s plus 12. Okay, so this is our transfer function and we want to represent it in first canonical form. So what do we do in first break it. So this g of s is equal to y of s upon u of s. Okay, this is s plus 2 upon s cube plus 3s square plus 6s plus 12. What we do is we write it as y of s into z of s into z of s upon u of s is equal to s plus 2 into 1 upon s cube plus 3s square plus 6s plus 12. Okay. So what we do is we have written y of s upon z of s is equal to s plus 2 and z of s upon u of s is equal to 1 upon s cube plus 3s square plus 6s plus 12. Okay. So now what do we do? We will consider this transfer function z of s upon u of s, which is equal to 1 upon s cube plus 3s square plus 6s plus 12, and we will cross multiply. So this becomes s cube into z of s plus 3 into s square into z of s plus 6 into s into z of s plus 12 into z of s. This is equal to u of s. Okay, this is equal to u of s. So now how will we proceed now? We will consider z of s to be equal to x1. S into Z of S is equal to x2, which in actual reality is x1 dot, right? S square into Z of S is actually is x3, which is actually x2 dot. Okay. So then what we will do? So then my S cube Z of S is actually x3 dot. Okay. So now we write the state space representation. We have x1 dot is equal to x2, x2 dot is equal to x3, and your x3 dot, which is this x3 dot plus 3 into s square z is equal to 3x2 plus 6 into s into z is actually your the 3x3. 6 into s into z is x2 plus 12 into z is your x1 is equal to u of s. Okay, so your x3 dot is minus 12x1 minus 6x2 minus 3x3 plus u. So this has been achieved. This is well and good. Now, how do we write this as? We write the vector x dot is equal to ax plus bu. So this is actually your x1 dot, x2 dot, x3 dot is equal to x1 dot actually is equal to x2. So it will be x1, x2, x3. So x1 dot is actually x2. So this is 0, 1, 0. X2 dot actually is x3. So it is 0, 0, 1, x3. And x3 dot is minus 12x1 minus 6x2 minus 3x3. That's why it is minus 12 minus 6 minus 3. And u comes only in the last. So it is 0, 0, 1 into u. Okay, 0, 0, 1 into u. So we have got our A matrix. We have gotten our B matrix. But then we have not got our output. So we have y of s upon z of s actually is equal to s plus 2. This is equal to s plus 2. So how do we tackle this then? So my y of s actually is equal to s into z of s plus 2 into z of s, right? So actually my y is actually x2 plus 2x1. Okay. So y, which is actually cx plus du. So the y actually is 2, 1, 0 into x1, x2, x3 plus 0 into u. So, and this is my C matrix. This is my D matrix. Okay. So this is the equation which I found, which is represented in first canonical form. And now how do we check whether the equations we got are matching what we consider? Okay, so let me do it. So what we will do is we are considering canonical form 1. Okay. So we'll have to write the A matrix which we got. That actually is A which we got is 0, 1, 0, 0, 0, 1, minus 12, minus 6, minus 3. So 0, 1, 0, 0, 0, 1, minus 12, minus 6, minus 3. This A matrix, B matrix is 0, 0, 1, the transpose of this. And C matrix is, I think, 2, 1, 0. So C matrix is 2, 1, 0. 2, 1, 0. So again, we use this formula G. And now let me run this section. So here it should be 3 because it's a third order. So I run it. It's come a whole lot bigger. The command bal reduction. So we got it. Okay. So we got the transfer function to be s plus 2 upon s cube plus 3s square plus 6s plus 12, which is the transfer function which we had originally used, from which we derived these canonical state space representation. First canonical state space representation. Okay. So I hope there's no doubt in this. So the A matrix, okay, let us see, sorry. This is s cube plus 3s square plus 6s plus 12. If you see the A matrix, it is minus 3, minus 6, minus 12. Okay, so from this you can get an idea roughly. So these are actually are the coefficients of your characteristic polynomial, and they are appearing in the last row of the A matrix. Okay, so this you can also use to check whether your uh, representation is correct or not. Okay. So now we have to do the second canonical form. We use the same transform function. G is equal to s plus 2 on s cube plus 3s square plus 6s plus 12. So this actually is your y of s upon u of s, right? So we will cross multiply. S plus 2 into u of s is equal to s cube plus 3s square plus 6s plus 12 into y of s. So s cube into y of s plus 3 into s square into y of s plus 6 into s into y of s plus 12 into y of s is equal to s into u of s plus 2 into u of s. This is represent, we consider terms of s cube. So s cube into y of s plus s cube into 3y of s, right? Plus s into 6y of s minus u of s plus 12y of s minus 2 u of s is equal to 0. Okay, so this is the representation. Then what do we do? We will consider y of s be equal to x1 of s, and x2 of s is equal to 3 into y of s. Okay, then x3 of s is equal to 6 into y of s minus u of s, right? Okay, I made a mistake. What do we do actually is consider x1 equal to y, x2 is equal to x1 dot plus 3y, and is this. Then x3 is equal to x2 dot plus 6y minus u, 6y minus u, and x3 dot plus this. Plus 12y minus 2u is equal to 0. Okay, so this is how we represent it. Okay, and then now what we do then? So x2 is equal to what? x1 dot plus 3y is actually 3x1. x3 is what? x2 dot plus 6y is what? 6x1 minus u. And x3 dot is equal to minus 12y plus 2u. So it is actually minus 12x1 plus 2u. So we rearrange these equations again. So we have x1 dot is equal to minus 3x1 plus x2, x2 dot which is equal to minus 6x1 minus 6, x2 dot is equal to minus 6x1 plus x3 plus u, and x3 dot is equal to minus 12x1 plus 2u. Okay, and we also know that our y is equal to x1. So how do we represent it as x dot? Okay, which is actually your x1 dot, x2 dot, x3 dot is equal to a, that is into x1, x2, x3 plus b into u. So what is x1 dot is minus 3x1 plus 1x2 plus 0x3 plus 0u. x2 dot is what? Minus 6x1 plus 0x2 plus 1x3 plus 1u. x3 dot is what? Minus 12x1, 0x2, 0x3 plus 2u. Okay, so this is the A matrix, this is the B matrix, and we know our y is equal to cx plus du. So y is what? 1, 0, 0, x1, x2, x3 plus 0 into u. So this is our D, this is our C. Okay, why is this happening? Because we know y is equal to x1. Okay, because y is equal to x1. Okay, so now if you see in this case, these are coming here. In the second canonical form representation, this minus 3, minus 6, minus s12, the coefficients of the characteristic polynomial are coming in the first column. Okay, so again, we will just try to verify our answer using MATLAB. Okay, so we have canonical form 2. What is our A matrix? A matrix is here minus 3, minus 3, 1, 0. So minus 3, 1, 0. Then in the second row, it is minus 6, 0, 1. So minus 6, 0, 1, 1. And in the third row, it is minus 12, 0, 0. Okay, so this is the A matrix. The B matrix is 0, 1, 2. So B matrix is what? 0, 0, 1, 2, and the transpose of it, because it should be a row vector. C matrix is 1, 0, 0, 1, 0, 0. Okay. So now let us find the transfer function of this system. Okay. Let me run this section. And again, we get the same original equation. That is g is equal to s plus 2 upon s2 plus 3s square plus 6s plus 12. Okay, so it remains the same. So okay, so now we have done two state space representation of the system. Now let us consider third form, which is known as the Jordan form. So in this case, let us consider transform function g, which is given by 1 upon s plus 3 into s plus 4. Okay, let us consider this system. Okay, I made it very simple. So this in partial fractions, we convert it into partial fractions first. So this is becomes what is equal to, okay, let me make it more difficult. Let us write s plus 2 over here. Okay. So this in partial fraction form, what do we make it? Write it as a upon s plus 3 plus b upon s plus 4. Okay, it is written like this. So we have to use partial fractions, right? We are using partial fractions. So what is my AB? So the s plus 2 is equal to a into s plus 4 plus b into s plus 3. Okay. So we need to find the values of a and b. So what do? We first eliminate b. How do we eliminate b? We eliminate b by putting s is equal to minus 3. So minus 3 plus 2 is equal to a into minus 3 plus 4 is equal to a. So we get a is equal to minus 1. Then we eliminate a. How? If we put s equal to minus 4. So minus 4 plus 2 is equal to b into minus 4 plus 3. So minus 2 is equal to b into minus 1. So b actually is equal to 2. Okay, so b is actually equal to 2. Okay, so there's a very simple method which is there, right? So what is our system now? Our system g of s, which is actually equal to s plus 2 upon s plus 3 into s plus 4. We are representing it as minus 1 upon s plus 3 plus 2 upon s plus 4. Okay, so this is my y of s output upon input u of s, which is equal to minus 1 upon s plus 3 plus 2 upon s plus 4, right? So what is done in such a scenario? You must note down that the poles are distinct, okay, and they are not imaginary. They do not have complex, they're not complex conjugates, etc. So what do we do now? Over here, okay, we represent it as y1 of s of u of s is equal to 1 upon s plus 3 and y2 of s upon u of s is equal to 1 upon s plus 4, right? Okay, we actually write it as, sorry, so this actually write it as x1 of s of u of s and this x2 of s of u of s. So then, how do we decompose this? And what actually is my y of s? My y of s upon u of s actually is equal to minus of x1s of u of s plus 2 of x2 of s of u of s. So we know y of s now in this case is minus x1s plus 2 x2 of s. Okay. So this is simple. Now what do we do is, we know x1 of s of u of s is equal to 1 upon s plus 3. So how do we write it as? We cross multiply again x into x1 of s plus 3 into x1 of s is equal to u of s. So we get x1 dot is actually minus 3x1 plus u. Similarly, if we consider x2 of s of u of s is equal to 1 upon s plus 4 then we will get x2 dot is equal to minus 4x1 plus u. Okay, so now when we will, so how we can write it as x1 dot x2 dot is equal to minus 3. Okay, this in terms of x1, x2 plus b into u. So x1 dot is minus 3x1 plus 0 into x2 plus 1 into u, and x2 dot is actually minus 4x2. Okay, this is minus 4x2. So 0 minus 4x2 plus 1 into u. Okay, so this is our A matrix and this is our B matrix. Okay, so now we have gotten our A and B, right? So we write now we also have y of s. Y of s is what? Minus x1 of s plus 2x2 of s. So it is minus x1 of s plus 2x2 of s. So y of s is equal to, in terms of x1 and x2 plus into u. So y actually is equal to minus 1 into x1 plus 2 into x2 plus 0 into u, right? So over here now, this is the C matrix and this is the D matrix. Okay. So how do we actually represent in terms of a block diagram form? Like how we visualize it in terms of a state space model? Like there's a method we use, okay, which is used. So this is your integrator. Okay, this is your integrator. The input to your integrator is your x1 dot. The output of your integrator is x1, right? Similarly, this is another integrator. The input to your integrator is x2 dot. The output is x2. Hmm? So what do we have the equation of x1 dot? X1 dot is minus 3x1 plus u. So x1 dot actually is equal to this is 3. Okay, minus 3x1 and this is 1 into u. X2 dot actually is equal to minus 4 into x1 plus 1 into u. Okay. Now what is my y? Y is minus x1 plus 2x2 plus 0 u. This actually is minus x1 plus 2 into x2. Add them. This is your y of s. This is your u of s. Okay. So this is kind of a way that is used by control system engineers to represent a system. The kind of like a block diagram form. So you can see the input is connected to each state x1, u of s, and output is coming combination of these states. Okay. And if you will observe the matrix A, this has these parts, okay, minus 3 and minus 4. So these actually are your eigenvalues of your system A, system matrix A. These are actually the eigenvalues. Okay, so let us check whether we get the same transfer function using MATLAB. Okay. This is for the Jordan form. So now our A in this case is minus 3, 0, 0, minus 4. Now B is 1, 1, transfers of it, and C is minus 1, 2. Okay. Now G in this case is C into S into EY of 2. Okay, because it is second order minus A. Sorry, it should be the inverse of it. Inverse of Si minus A into B. Okay, so let me run this section. So this comes as S plus 2 into S square plus 7S plus 12. And if you expand S square plus 7S plus 12, it actually is S plus 4 into S plus 3, which was what we started with. Okay, so our representation in this form is correct. Okay. Now let's consider a case when there are repeated poles. Okay. We consider case S plus 3 into S plus 2 square into S plus 5. Okay, this is our system. Now, how do we represent the system as? We represent it as A upon S plus 2 plus B upon S plus 2 the whole square plus C into S plus 5. Okay, C into S plus 5. So now we need to find the values of A, B, and C. So we write S plus 3 is equal to A into S plus 2 into S plus 5 plus B into S plus 5 plus C into S plus 2 the whole square. So now we put S equal to minus 5. What we will get? Minus 5 plus 3. Okay, because S plus 5 is that becomes 0, 0. So it becomes C into minus 5 plus 2 the whole square. So this minus 5 plus 3 is minus 2. Minus 2 is equal to C into minus 5 plus 2 square is minus 3 square. So C into 9. So this means your C actually is minus 2 by 9. Next, what do we do is we put S equal to minus 2. Then what we get is minus 2 plus 3 is equal to A into S plus 2 becomes 0. And again C into S plus 2 square becomes 0. So this is B into minus 2 plus 5. So we get 1 is equal to B into 3. So this means the B actually is 1 by 3. Okay, so we have gotten B is equal to 1 upon 3. Now we need to get A. We need to get A. So what I do in this case is I'll put S is equal to 0. So we get 3 is equal to A into 2 into 5 plus B into 5 plus 4 into C. So that means 3 is equal to 10A. B is what? 5 by 3. C 4 into C. So it is 4 into minus 2 by 9. Okay. So it is 10A plus 10 up 10A plus 5 by 3 minus 8 upon 9. This is converted as 3 is equal to 10A plus 15 minus 8 upon 9. So 3 is equal to 10A plus 7 upon 9. 10A is actually 3 minus 7 upon 9. That is 27 minus 7 upon 9. So that actually is your 20 upon 9. So now A actually is what? 2 by 9. So we get A is equal to 2 by 9. B is equal to 1 by 3. And C is equal to minus 2 by 9. Okay, these are the numbers which I have got from the partial fraction expansion. So now what we get, g of s is 2 upon 9 upon s plus 2, okay, plus b upon s plus 2 square. So 1 upon 3 upon s plus 2 square plus c upon s plus 5. So plus minus 2 upon 9 upon s plus 5. Okay, so this is the representation. So now how do we go about this? Okay, so it is simple to make what you say, this x1 of s upon u of s be 1 upon s plus 2, and this x3 of s of u of s is 1 upon s plus 5. So these are very simple. So what do we get this as? X1 dot is minus 2x1 plus u. This x3 dot is equal to minus 5x3 plus u. Okay, these are simple. But what is difficult is this term. X2s upon u of s is equal to 1 upon s plus 2 the whole square. So how do I tackle this? Okay, this is for this. Okay, this is for this for this. So how do we tackle this? So this is written as, sorry, it is written as actually 1 upon s plus 2 into 1 upon s plus 2, right? So x2s upon u of s is equal to 1 upon s plus 2 into what? X s 1 upon s plus 2 is what? X1s upon u of s. So what happens now? This u of s gets cancelled. So we get x2s upon x1s is equal to 1 upon s plus 2. So what do? We cross multiply. It becomes s into x2 of s plus 2 into x2 of s is equal to x1 of s. So we get x2 dot plus 2 into x2 is equal to x1. So which we can further write it as x2 dot is equal to x1 minus 2x2. Okay. So then we combine all the equations. We got x1 dot is equal to minus 2x1 plus u. X2 dot is actually what? X1 minus 2x2, and x3 dot is equal to minus 5x3 plus u. So this is written again in a combined form. X1 dot, x2 dot, x3 dot is equal to, in terms of x1, x2, x3, and u. So x1 dot is what? Minus 2x1 and 0, 0 of x2, x3 plus 1 into u. X2 dot is what? X1 minus 2x2 plus 0x3 plus 0u. And x3 dot is 0, 0 minus 5x3 plus 1u. Okay. So this is the transfer function. This is the state space representation. And so this is our A matrix. This is a B matrix. Now I have to find the output. So the output is what? Y of s. So this is equal to your y of s upon u of s, right? So y of s upon u of s is actually equal to 2 by 9, 1 by 3, and minus 2 by 9. So this is actually 2 by 9 into x1 of s upon u of s plus 1 by 3 into x2 of s upon u of s and minus 2 upon 9 x3s upon u of s. So what it becomes? Y of s is what? 2 by 9 x1s plus 1 by 3 x2s minus 2 by 9 x3 is, so y is 2 by 9 x1 plus 1 by 3 x2 minus 2 by 9 x3. Okay, so what do we get? Y is 2 by 9, 1 by 3 minus 2 by 9 into x1, x2, x3 plus 0 into u. Okay, so this is the C matrix and this is the D matrix. All right. So again, as is our normal custom, we will write it in terms of matrices and just check the transfer function to check if our answer is correct. So the A matrix is given by A is, sorry, A is my minus 2, 0, 0, then 1, minus 2, 0, and then 0, 0, 5. Okay, so this is A matrix 0, 0, minus 5. 0, 0, minus 5. The B matrix is given by 1, 0, 1, the transpose of that. And C matrix is given by, C matrix is given by 2 by 9, 1 by 3, minus 2 by 9. So it is 2 by 9, then 1 by 3, then minus 2 by 9. Okay, so these are C matrix. So G is again given by this formula. But in this case, it is a 3-dimension. So 3 should be here. Let us run this section. So it comes out in this format. 3 bad thing should be done. Run this section. Okay. So it comes in this format: s plus 3 upon s square plus 9s square plus 24s plus 20. Right? Which is similar to what we have, right? So our system is s plus 2 square into s plus 5. So actually g of s is s plus 3 upon s plus 2 square into s plus 5. So this is equal to s plus 3 upon s square plus 4s plus 4 into s plus 5, which is equal to s plus 3 upon s cube plus 4s square plus 4s plus 5s square plus 20s plus 20. So this is equal to s plus 3 s cube plus 9s square plus 24s plus 20. Okay, which is what we got over here. Thus, we can see they are equivalent. So another thing I'd like to point out is why I need to use this Bell rate. So Bell rate is used for reduction of the size, reduction of the order of the transfer function. So sometimes MATLAB actually may have some certain computational errors or certain approximations it would have taken, or some values is coming e to power minus 30 something, which we don't want. Let us see over here. If you see this, it is coming minus 1.388 into e to power minus 16 s cube. Okay, so this can be neglected. This is not the actual value. Okay, this actually is almost 0. So that's why to get rid of it, what we do, we use this. So that we know our system should be third order, right? But MATLAB is giving fourth order. So what we do, we tell MATLAB that explicitly you find a transfer function with giving the information that my system transfer function will come third order. And then it is able to give you the correct transfer function. It is accurate. Okay, it is accurate. Okay, so these are certain commands which are useful, which I hope you will be using it in your assignments and in everything. So why I want to bring in MATLAB is so that you can check what are the answers you're getting, whether it matches. You are given a transfer function, You find a state space representation. You find the ABCD matrix. Like in the assignment, there'll be a question. You find the state space representation of this transfer function in canonical form 1 or canonical form 2 or in Jordan form, and you find a representation and you select the option. But then you don't know whether what you got actually is correct or you have made a sign error or some error, right? So this is a way for you to verify your answer. Okay, this is just a way. Okay, you can use it or you can not use it. It depends if you have MATLAB license, etc., so that you can use these lines of code. Okay, but it's a very simple line of code, which I'm just repeating it. So I just have to have the matrices and then it can proceed with it. Okay. Okay. So now we'll see about the conversion of state space forms. As I said, x dot can be equal to ax plus bu and y is equal to cx plus du. Okay, this is given to us. But what if we represent it in terms of state z? And this z dot is actually equal to a bar into z plus b bar into u, and y is equal to c bar into z plus d bar into u. And both of these have the same transfer function. So they will have the same transfer function. They will have the same characteristic equation or characteristic polynomial. Also, right? They have the same transfer function. They have the same characteristic equation. They have the same poles. Okay. But then how do I convert a into a bar? Right? There should be some method. So we consider that there is what is known as a transformation matrix T. It is given by x equal to t into z. So the transformation matrix T is a dimension n cross n. So this is square matrix. Okay. And another thing is it should be invertible. T must be invertible. Okay. So how do we get it as? What we do, we already have, x dot is equal to ax plus bu. Okay. We substitute x is equal to t into z. So what do we have? T into z, the derivative of that. So to a, x is again t into z plus b into u. Now since t is like a constant transformation, so what happens? It comes here. T into z dot is equal to a into t into z plus b into u. So this is it. What do we do then? We pre-multiply both sides by t inverse. That is why t should be non-singular. It should be non-singular. That means its inverse must exist. So z dot, so t inverse into t is equal to z dot into t inverse a t plus t inverse b u. So that means z dot is equal to t inverse a into t. Sorry, this is x, not x. This is z. Sorry, this will be z plus t inverse b into u. So z dot, which is actually a bar into z plus b bar into u. So the a bar can be found by t inverse a t and b bar is equal to t inverse b. Okay, b bar is equal to t inverse b, right? And y is actually cx plus du, right? So we substitute x, so it is c into t into z plus d into u. So that means y is equal to c bar into z plus d bar into u. So now what is our c bar? C bar is c into t and d bar remains d. Okay, it does not change. All right, so this is how we can convert one state to another state, all right, using this method. Okay, so lecture 5 deals basically with the Jordan form. Okay, this is how the poles come in the diagonal form if they are not repeated. These are the residues of those poles, and this is the C matrix which comes like this. Okay, and if they are repeated with multiplicity n, then what should be done? Which we also did. We solved one example, and sir also has solved this example. So that is over here. So let's solve this example. So we did a similar example. We solved. Okay, and we checked. We got the correct answer. Okay. So this is what sir taught in lecture 4 and 5. First companion form, second companion form, Jordan form, etc. So now let us go to lecture 6. So what happens is we choose the physical variables of the system as a state variable. Like in the series RLC system, we consider the inductor current and capacitor voltage as the states, right? Because they are easier. They actually represent something very significant of the system which we can understand, which we can measure, etc. So that's why we choose those as our state variables. But sometimes it might be necessary for us to represent this system in some particular canonical form or some other form such that it become easier for us to analyze the system, to check the properties of the system. That is why there are various canonical forms, right? And there should be a way to transform one form to another form. Okay. So that's what it is written, that one form of representation is preferable to the other form so that it is easier to interpret of analysis and all. So this is our state space model, and here sir has done the derivation which I just showed how we got those variables. Okay. So what happens is x dot equal to ax plus bu and y equal to cx. It is transformed into an equivalent model where z dot equal to a bar z plus b bar u and y is equal to c bar z. Okay. So this is a simple way. So where's it? So this is the system. X dot is equal to ax plus bu, y is cx. And now using the transformation matrix, we need to find a new updated uh, state space matrices of that model. Okay. So how do we proceed with that? How can we solve this thing? Okay. So let us try to solve it in MATLAB. Let us make our life easy. So transformation of system representation. So this is the original system, A original. What is it given by? -1, 0, 0, -2. And B is given by 1, -1. So 1, -1. Okay, and C is given as 1, 1. 1, 1. Okay, the transformation matrix T, okay, the B original, this is C original. Transformation matrix T is given by this matrix. They have given the matrix. That is 2, 1, and then minus 1, minus 1, minus 1, minus 1. So there's a transformation matrix. So now what is the new updated or new A matrix should be given by inverse of T into A original into T. Okay, this is a matrix which we want. So let us run this section. So A new comes out to be 0, 1, minus 2, minus 3, which is shown over here 0, 1, minus 2, minus 3. B new, that is inverse of T into B. Okay, so let me run this. Okay, into B original. That is 0, 1. So which comes out to be 0, 1. And C new equal to C into T. Okay. So that if we run it, oh, C original, C underscore original. So this comes out to be 1 and 0. Okay. That is again this 1 and 0. Okay, so we got the equivalent state space model in terms of the state variable Z. It's a very simple code which was used, and I hope you guys will understand the importance of that and do it. Okay. Okay. So now let us find what is a characteristic polynomial. Okay, there is a code. This is a characteristic polynomial of A original in terms of x. Okay, in terms of x, let us see. Let us find a characteristic polynomial of A. Okay, we have to define. Okay, so let me write something. So we want to find a characteristic polynomial. Okay. So we want to define some variable x. We will use the symbolic toolbox if you have, and I'll define a variable x. Okay. Now I'll run this code. It will give okay. It is giving this is the characteristic polynomial, that is x square plus 3x plus 2. Okay. Let us manually calculate so that you will understand the power of this. Okay. So this was my A, right? This was my A. The original A was given by minus 1, 0, 0, minus 2. Minus 1, 0, 0, minus 2. So statistic polynomial is what? Si minus A, the determinant of this, right? That is what determinant of S 0, 0, S minus A. So minus 1, 0, 0, minus 2, right? So that is what S plus 1, 0, 0, S plus 2. So this Si minus A is what? S plus 1 into S plus 2. That is S square plus 3S plus 2. Right? And what are we getting here? X square plus 3x plus 2. Okay, so this is a easy way, okay, to get the characteristic polynomial. Okay, let us try if I use the variable s. Let us try if I use character poly a underscore original s. Did it work? Okay, s is a transform function, so it doesn't take it. Okay, now let us find what is the characteristic polynomial for the new converted. Okay, for a new. So a new comma x. Okay, so let me run this section. What do I get? Again, I get the same thing. So that means for both, I'm getting x square plus 3x plus 2. So for both the original matrix A matrix and the converted A matrix, the characteristic polynomial is the same, and hence the poles or the roots of the characteristic polynomial remain the same, right? So this we have considered. They are equivalent. They're the same characteristic equation which I showed. As I've been showing multiple times, they will have the same transfer function. Okay. So this is just a proof of it, which you can see. Okay, they have the same transfer function also, sir has shown. All right, so now let us go to lecture 7. Okay. So we got state space representation in various canonical forms. And a given state space representation can be converted into other canonical forms, right? So how do we do that? If you want to convert it into diagonal form, okay, if you want to convert it into Jordan form, well, how can we do it? Or how do if you want to convert it into canonical companion form, then what to do? Okay. Suppose this is a state equation, x dot equal to ax plus bu, and it can be transformed into this z dot equal to gamma z plus beta u. Okay, we have to make sure that the eigenvalues of A are distinct. Okay, what are the eigenvalues? What are the eigenvectors? We will see. Okay, so how do we do this thing? How do we get it? Okay, is there a sum? Is there an example? We'll check. Yeah, there's an example is given. So we will see this. Okay, so this is the example. We want to convert into diagonal form. So what do we have? A is equal to minus 1, 1, 1, minus 1, 1, 1. Then we have 0, minus 2, 1. Then we have 0, 0, minus 3. Okay, so this is the A matrix. Now what do we do with this A matrix? We have to first find the eigenvalues of this A matrix. So eigenvalues are found by doing lambda I minus A. So what is this? Lambda into 1, 0, 0, 0, 1, 0, 0, 0, 0 minus A, that is minus 1, 1, 1, 0, minus 2, 1, 0, 0, minus 3, right? So this is lambda 0, 0, 0, lambda 0, sorry, this should be 1. So this is 0, 0, lambda, okay, minus 1, 1, 1, 0, minus 2, 1, 0, 0, minus 3. So this is equal to lambda plus 1, minus 1, minus 1, 0, lambda plus 2, minus 1, 0, 0, lambda plus 3. Okay, so this is the matrix. Now we want to find the eigenvalues. So that we will do lambda I minus A. That's what lambda plus 1 into what? Lambda plus 2 into lambda plus 3. Okay, minus 1 into minus 1, so plus 1 into 0 into 0, 0, 0, so 0. Then minus 1 into 0, 0, so it is 0. So this is lambda plus 1 into lambda plus 2 into lambda plus 3. That means your lambda is what? Minus 1, minus 2, minus 3. So an easier way for you to recognize is if you can see this is an upper diagonal. Okay, it is in upper diagonal form. So if it is either in diagonal form, okay, this one is in upper diagonal form. So if it is either in diagonal form, upper diagonal form, or lower diagonal form, then what do we know? That these elements, these diagonal elements of the matrix are the eigenvalues. Okay, these are the eigenvalues. Now, what we get is these are distinct. They are different. Okay, that is what we want. Then only we can get it into a diagonal form. Okay, this is the trick. We have, if you want to get it in diagonal form, then all these eigenvalues should be distinct. If it is not distinct, it is not possible. Okay, so first we establish that they are distinct. Now what do we do? Now we have to find their eigenvectors. How do you find their eigenvectors is, you have to do lambda into I minus a into the eigenvector v bar is equal to lambda into v bar. Sorry, equal to 0. Okay, because I have taken it in the left side. So let us do with lambda equal to minus 1. Okay. So lambda 1 is equal to minus 1, and then we have v1. Okay, v1 we will give it the values v11, v12, v13, etc. Okay, so so if you put minus 1 over here, so we get 0. We get 0. Then we get minus 1, minus 1, minus 1, minus 1, 0. Lambda plus 2 is 1. And then over here it is 1, so minus 1, minus 1, 0, 0, lambda plus 3. So if it is minus 1 plus 3, so 2 into v11, v12, v13 should be equal to 0, 0, 0. Okay. So if we see this equation, what do we get? Minus v12 minus v13 is equal to 0. And we have v12 minus v13 is equal to 0. And v13 is equal to 0. So if you look at all these equations, if you solve this and this, what you get? You get here v12 is equal to v13. And here you get v12 is equal to minus v13. So how is this possible? These two are possible only when v12 is 0 and v13 is 0. And here we have already proved that v13 is 0. So our eigenvector v1 bar actually is equal to 1, 0, 0. We give some number value v11. So v11 is 0, 1, 2, 3, 4, any value. These equations will be satisfied. Okay. So that is why we will take a simple value. So we take 1, 0, 0. So this is the eigenvector we are looking for. Okay. So actually the eigenvector, so this is the eigenvector. They are actually representative of a certain direction which is inherent in the matrix. Okay. So they have a very good, great geometrical perspective. Okay. So which might be touched upon further on in the course. Okay. But for just for your knowledge, I'm saying that. Similarly, we can find another eigenvalue. So lambda 2i minus a into v2 bar. This should be equal to 0. So this will be minus 1, minus 1, minus 1, 0, 0, minus 1, 0, 0, 1 into v21, v22, v23 is equal to 0, 0, 0. Okay. So now what do we see over here? So we have minus v21, minus v22, minus v23 is equal to 0, and minus v23 is equal to 0, and v23 equal to 0. Okay, so what we have found is v23 is equal to 0. This is established. This is very clear. Now we have minus v21 minus v22 is equal to 0. So what do we consider in this case? v21 is equal to minus v22, right? So v2 bar, we take it as 1. v22 is minus of that. 1 minus 1, 0. So this is our v2 bar eigenvector. Now we have to find the third eigenvector, right? So we have to do lambda 3 into I minus A into V3 bar is equal to 0. So that is what minus 3 minus 1, right? That is what lambda plus 1, right? So lambda plus 1, so lambda is minus 3. So minus 3 plus 1 is minus 2. So this is minus 2 minus 1 minus 1, 0. So minus the lambda is minus 3. So minus 3 plus 2 is minus 1 minus 1. Then you have 0 0 0, right? Into V31 V32 V33 is equal to 0 0 0. So what we get here? We get minus 2 V31 minus V32 minus V33 equal to 0 and minus V32 minus V33 equal to 0. So how do we solve it? So we get V32 is actually equal to minus V33. So the simple method what is used is we assume V33 is some t, okay, some constant t. So what do we get? V32 is equal to minus t, right? And then what do we have? We have minus 2 V31 is what? V32 plus V33. So this is equal to what? T and minus t equal to 0. So V31 is equal to 0. So V3 bar actually is equal to 0 minus t. So we take t outside, so it comes 0 minus 1 1. So we actually eliminate t. So we write finally here V3 bar is 0 minus 1 1. Okay, so this is our third eigenvector. Okay, so I hope it is clear how do we find the eigenvector. So the eigenvector concept is a bit tricky and hard and difficult, but I hope you guys have understood. You can also ask questions and doubts in the comment section also. And I will show how do we get these eigenvalues easily. Okay. And how do we get the eigenvector also? Just check to verify what is this, whether we got the correct answer or not. So now we form the transformation matrix, which is given by V1 bar, V2 bar, V3 bar. Okay. So what is our V1 bar? V1 bar, actually, I think if I'm not wrong, it is 1 0 0. So V1 bar is 1 0 0. So it is 1 0 0. V2 bar is 1 minus 1 0. So that is 1 minus 1 0. And V3 bar is 0 minus 1 1. V3 bar is 0 minus 1 1. So this is our transformation matrix. So now what our A diagonal matrix also represents lambda is what? V1, V inverse A into V. Okay, so V inverse A into V. So these mathematical calculations are very long, take lots of time. Okay, but let's try it. So now we want to find V inverse, right? So V inverse is what? 1 upon V into adjoint of V, right? Or yeah. So what the adjoint of V actually we find in a way adjoint of V transpose we get it as, so 1 we, if it's this element we will consider there it's minor. Okay, so minus 1 into 1 minus 1 into 0 is 0, so then minus 1. But here it is 1 into, let me do simple. First is minus 1 into 1 plus 1, first row first column, into its minor, so minus 1 into 1, so this is minus 1. But here we do minus 1 into 1 plus 2, first row second column. So for this we will consider what? These two and these two. So that we will write it as, and since it is 0 into 1 and 0 into minus 1, it is 0. So it is 0. For this one, okay, for this one, it will be minus 1 into 1 plus 3, again 0 into 0. Now in this case 0, it is 1 into 1 into 0 into 0. It is minus 1 into second row, first column into 1. Right? Here it is minus 1, second row, second column into 1 into 1, 0 into 0. So it is 1. Here this second row, third column, that means this one. So it is 1 into 0, 0 into 1. So it is again 0. Now we will come to this column. It is minus 1 into 3 plus 1. It is 1 into minus 1, and minus 1 into 0. So it is minus 1. When you come to this, it is this and this. So actually it is minus 1 into 3 plus 2. 1 into minus 1, 0 into 0. So it is again minus 1. And when you come over here, it is minus 1 into 3 plus 3. So it is 1 into minus 1, 0 into 1. So it is again minus 1. So this actually is equal to minus 1 into 1 plus 1 is minus 1 square. So 1. So 1 into minus 1 is minus 1. This is 0. This is 0. Minus 1 into 2 plus 1 is minus 1 raised to 3. So it is minus 1. So this is minus 1. Minus 1 into 2 plus 2 is minus 1 raised to 4. So this plus 1 into 1 is 1. This is again 0. So here minus 1 into 3 plus 1 is 1 into minus 1. So it is minus 1. Here minus 1 raised to 3 plus 2 is minus 1 raised to 5. So it is minus 1 into minus 1. So that is 1. Minus 1 raised to 3 plus 3 is minus 1 raised to 6 into minus 1. So this is minus 1. Okay, so this is adjoint of V transpose. So our adjoint of V actually is minus 1, minus 1, minus 1, 0, 1, 1, 0, 0, minus 1. Okay, so this is what we got. So now, what we have to do now? Now we have all this information. Now, how do we proceed? So V inverse is 1 upon determinant of V into adjoint of V, right? So what is V? Determinant is 1 into minus 1 into 1, so minus 1. And minus 1 into 0, 0 into 0. So actually it's minus 1. So this actually is 1 upon minus 1 into this minus 1, minus 1, minus 1, 0, 1, 1, 0, 0, minus 1. So V inverse becomes equal to 1, 1, 1, 0, minus 1, minus 1, 0, 0, 1. Okay, till here we have got it. So now we will try to complete it. So our diagonal is what? V inverse AB. Okay, we'll leave V inverse first. What is A? A is minus 1, 1, 1, 0, minus 2, 1, 0, 0, minus 0. Okay, this minus 1, 1, 1, 0, minus 2, 1, 0, 0, minus 3. And what is V we got over here is 1, 0, 0, 1, 0, 0, 1, minus 1, 0, 1, minus 1, 0, and 0, minus 1, 1, and 0, minus 1, 1. Right? So this is V inverse. So if you cross multiply, this will become minus 1. Here, if you do minus 1 into 1 plus 1, minus 1, so minus 2, right? Over here, if you do, it comes out to be minus 2 again. 1 minus. Here it is actually minus 1 and minus 1, so minus 2. And in this case, it is minus 1 plus 1 to the 0. It is 0. Now for here, it is 0 into 1 and 0, 0. So it is 0. 0 into 1 is 0. Minus 2 into minus 1 is 2. And here it is 0. 0 into minus 2. So this minus 2 minus 1 is 2. Plus 1 is 3. Okay, here 0, 0. So 0, 0 go here. 0 again here. So 0. Again here to 0. 0, 0 minus 3. It is minus 3. Okay. So now we have to multiply it with V inverse. That is 1 0 0, 1 minus 1 0, and 1 minus 1 1. Okay, into minus 1 0 0, minus 2 2 0, 0 3 minus 3. Okay, so this is 1 into minus 1 and minus 2 into 1, so this actually is minus 1. Then minus 1 into minus 2 plus 2, so this is 0. This here 3 minus 3 again is 0. Now here 0 into minus 1 is 0, into 0 0, so it is 0. 0 into minus 2 0, minus 1 into 2 is minus 2, and again into 0. 0 into 3 0 0, minus 3 and plus 3, so again it is 0. So now again here it is 0 0, here it is minus 3. Okay, so we got the diagonal matrix. Okay, using this transformation we were able to get the diagonal matrix. So now let us try in MATLAB. What we do is, sorry, diagonal the way. So what is the A matrix? The A matrix originally which we had was minus 1 1. Oh, here it is, minus 1 1 1, 0 minus 2 1, 0 minus 2 1, and 0 0 3, 0 0 3. Okay, so there's a A matrix. So let us run it. Let us run this section. So we run this section. The diagonal matrix is minus 1, minus 2, and 3. This is minus 1, minus 2, and 3. I think we have made a mistake. This is minus 3. Okay. We run this section again. So this is a diagonal matrix which we got. And these are the eigenvectors. So if we remember the eigenvectors which we got 1 0 0. And then we got V2 bar. You remember V2 bar, we got 1 minus 1 0. What they have got? Minus 0.7 upon 0.7. So now there's a confusion, right? We got what MATLAB has got. They have got V2 bar is actually minus 1 by root 2, 1 by root 2, and 0. But we got V2 bar as 1 minus 1 0. So who's right, who's wrong? If you see, this is a unity vector. It's a vector of magnitude unity. So ours is not a vector of magnitude unity. Also, there's a sign mismatch is there. So the V2 bar we have is actually minus root 2 into the V2 bar they have. So will it create any issue? As you can see, we have used the V2 bar which we have got and it didn't create an issue. So eigenvector basically points to the direction. So the direction is fixed. You can scale that vector by some amount or by some other amount that is upon you. But the eigenvector which you get has some direction. So this also has the same direction. This also has the same direction. But their magnitude is different. Okay? It is just different in magnitude. If you multiply it by minus 1, its direction is reversed. But the inherent property is that it is in one particular direction. Okay, so that's our V2 bar. Similarly, they got V3 bar as 0 minus 1 by root 2, 1 by root 2. What we got V3 bar is 0 minus 1 bar. So their V3 bar, which they got, actually is 0 minus 1 by root 2, 1 by root. So could we have got that value? We could have got. If we had put t is equal to 1 by root 2, then what we would have got V3 bar? We would have got 0 minus 1 by root 2, 1 by root 2. Okay. So now why didn't I choose this value? Why did I take 0 minus 1, 1? I chose this value because it becomes easy when I'm finding this inverse. Okay, when I'm finding this matrix V and this inverse, if I have this 1 by root 2 and multiply that and do, it is very complicated. It might be easier for the machine, for MATLAB to do the multiplication, etc. But for me, it is difficult. That is why I took the values of 1, 1, minus 1, 1, 1, 0, 0, etc. Okay. So that is something you can look into. Okay. And if you just want to find the eigenvalues, you have to just put EIG of A. It will give you the eigenvalues minus 1, minus 2, minus 3. Okay. And this is a diagonal matrix which we got. So thus we can say what we did was correct. Okay. It was right. All right. Okay. Further, sir has done this derivation and shown the V matrix, etc. If it has repeated eigenvalues, it cannot be transformed into diagonal form. It has to be transformed into Jordan form. Okay, that process is a little bit complicated and advanced. Similarly, Sir has also shown how to transform the state equation into companion form. Also has been shown by Sir. Okay, there's a ready-made procedure which you can use to get the values. Okay. Achha. So what is the method? Let us consider this one. We must take A and B matrix. Okay, so the A and B matrix which Sir has considered is A is 1, 2, 1, 2, minus 2, 1, minus 2, 1. This is A matrix, and this is a B matrix. Or so let's use B, small b, so we'll consider that. So that is 2, 2. So 2, 2. Okay, so this A and B. So what is your mu matrix? Q matrix is B and AB. So Q matrix is what? B and A into B. Let us run this section. What do we get? So Q is 2, 6, 2 minus 2. Okay. So we got similarly Q is 2, 6, 2 minus 2. If you want to find the inverse of Q, you will get this value, which is same as this. Okay, this is the inverse of Q. Now what is the step? We have to find V. So what is V is mu and mu A, that, right? So which is the mu we must take? So mu is taken as the second row of this. Okay. So mu is taken as this inverse of Q. Okay, let us store it as a value. Q inverse. Okay. Q inverse and the second row of it, right? Second row, both the columns. This is mu. So this is mu we got. Okay, this is the mu they have also got. And mu they have taken this value. So we have got 1 by 8 and minus 1 by 8. Here we have 1 by 8 and minus 1 by 8. See, correct. Now, AC. AC is given by what? In the steps, we have AC's. So V is equal to mu and mu A. Okay, so V is equal to mu and mu into A. So what is V? We got V, right? And then what do we have to do? AC, okay. Then inverse of V into A into V and inverse of V into B. This is a transformation. So we run this section, we get it in this form. Okay. And if you see over here, they have also got the same thing. So the AC is they have got a slightly different value, 2 1 minus 1 5 0, and B is 0 1. What was the issue? Hmm. Okay, V is the inverse. Okay. Sorry. This will be, let us say this is some variable U. Okay. So V actually is this inverse of U. Okay, so this is very complicated. This is our V. Okay, so let us run this section. So we get it. So A is 0 1 minus 5 2 and B is 0 1, which they have also got. 0 1 minus 5 2 and BC is 0 1. So this is the AC, and this is BC. Okay, so let me just, so this is the system matrices. These are the system matrices. We have to compute this matrix. Here we are finding inverse of Q. Then we select a row. Then we find inverse V, right? And then we find V. And then we use that to find AC and BC. These are transformed, where AC and BC are transformed state space representations, the canonical. Okay, so hope this is understood by you guys. So these are the steps which I hope you can understand. All right. Yeah, and I can share this code also. I think I'll have to upload it somewhere. Okay. So thank you. And if you have any queries, please comment in the YouTube video. Okay. Thank you.